Okay, so this obviously is a video for section 5.0b. As you hopefully know, 5.0a was just kind of a basic lesson about scatter plots and the different correlations that could be represented in a scatter plot. This lesson, obviously, with it being 5.0, but now B, there's going to be a connection to that, obviously, and it's going to be about lines of best fit. You can, if you have the handouts, you can probably see that. Speaking of the handouts, this video is actually going to include the warm-up first, then the sort of official 5.0b notes handout, and then another handout called just 5.0b scatter plot examples. So here's what the warm-up handout kind of looks like. Okay, hopefully you have that one with you on hand. Obviously this is the main official notes handout, and then I think in this video we're also going to go over this handout looks like this. So hopefully you have hard copies of all three of those with you as you go through this video. And with that being said, let's get started. So the warm-up, let's see here. I guess this first part isn't literally on the warm-up paper, so nothing to write, just kind of think to yourself, looking at this line and this, like the graph of this line, this graph, are you able to give the equation of this line? How do you take lines that you see graphed and come up with the equation of the line? What do we need to know, or what would we really like to know about this line? What would we really want to see in this graph with the line that you'd be able to write the equation? What two things would be amazing to know? Wouldn't one thing be the slope? And wouldn't the other thing probably be the y-intercept? Because if you remember slope-intercept form, y equals mx plus b, if you know what to put into the m and b positions, you can write your equation. Like there, you have an equation. So, I mean, look at this. This is definitely on purpose, how you look at this particular graph and try to come up with what the slope would be, as well as the y-intercept. Like, where is this line going to hit the y-axis? Well, just kind of a little demonstration here. Just showing, like, well, once we put a grid on here with it, as well as extending the line to where you know where it's going to hit the y-axis, now you'd be way in a much better position to look at this and go, oh, now I can figure out the rise over run, which is your slope, as well as just see that the y-intercept apparently, or obviously, is 5. And then the slope would be, let's see, 1, 2, 3, 4, 5 up, 1, 2 to the right. So it looks like the slope would be 5 over 2. So so your equation would just be, and again, I'm not going to write it down because you're not going to write it down either. But if you did it, you'd write down y equals, okay, y equals 5 over 2 x plus 5. So now we're getting into the handout. Can we do that? So it seems like one of the big themes here of this entire video, so kind of a spoiler alert, kind of or a sneak preview or whatever, one of the big ideas here in 5.0b is something that's not even new to us. You know, if you can look at a line, or if you're just told for free what the slope is of your line as well as the y-intercept, you can write your equation. Is that possible with this example here, number 1? Think we can figure out the slope? Yeah, probably. Like, there's a pretty nice point. I'm going to go ahead and say, well, that one just kind of seems really nice. And another sort of idea here that's going to be all throughout, is going to be a reoccurring thing, is when you're looking to calculate the slope of a line, and like you don't know exactly what points are on this line for sure, you just have to kind of trust your eyes and go, well, it looks like the line is containing this exact nice point with those nice integer coordinates, as well as this one. So anyway, if you're trying to calculate the slope and you have to figure out points, the farther apart the better to get an accurate slope. But I mean, it looks like maybe also this one, and therefore if let's see if this point and this point agree, you know, having this point be a point as well as this one. Again, the farther apart the better, but let's see if this point agrees, because if this is a point, look, up 2 over 3, then wouldn't that one have to be a point? Up 2 over 3, yes. Up 2 over, yeah, okay. So basically this point and this point, along with, they all agree that our slope is, you know, at the end of the day, 2/3. Okay, it looks like if you literally counted or did the slope formula with these 2 points, or the coordinates of these 2 points, you'd end up with like 10 over 15, but of course that just reduces to 2/3. So again, don't want to try to repeat myself too much in this video, but it's inevitable. You can calculate slope, as you should know. This is not new either. You can calculate slope by just counting the rise over the run, as long as you're very careful counting. Or you could do the formula where it's like the coordinates of this point or this point. But anyway, can we also figure out what the y-intercept is? Yeah, look at that. It's obviously, or maybe not obviously, but it looks like it's 5. So the y-intercept is 5, and that means that our equation is just going to end up being that, because of, you know, the beauty of slope-intercept form. So plugging in the 2/3 for m and the 5 for b, y equals mx plus b, that's the equation. Can we do the same thing here? Meaning, can we just figure out, that looks like a nice point, and I mean, that looks like a nice point. Maybe there's others. If we're going like down 5, it looks like, over, is it 10? From 30 to 40? Yeah, so we can figure out the slope. Can we figure out the y-intercept? Where is this line going to hit the y-axis? Ooh, that might be a problem. That might be a problem. Because look, the y-axis, it's, where is it? It's not even here. The y-axis isn't going to be showing up until like way over here to the left. So what are we going to do? Okay, what's our backup plan if we can't figure out slope and y-intercept? How else can we figure out the equation of a line? and again, this is not new to you either, if you know the slope, see, I don't know. So the answer is we're just going to use point slope form. So if we know the slope and a point, remember, we can do this formula. Y minus y1 equals m times the quantity of x minus x1. So it looks like I'm picking the point 30 comma 15 right here, but you could have used this one, and if our slope is negative 1 over 2, looks like that is a valid point. That'll work amazingly. So is that one, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. So there's a lot of points that seem to be nice and on the line. So you could have picked any point. I went with 30 comma 15. And something I've probably said in the past, if the directions aren't being very specific, just what's the equation? That's an equation. Okay, it's not like they were asking for a specific form for your final answer. So if you want to stop right there, I mean, no one can blame you. You know, in a court of law, like no one can say this is not a correct answer. But again, normally we like to distribute this through the bubble and then end up getting y all by itself for this final answer in slope-intercept form. Again, I've seen this in the past. Just because you can't start with slope-intercept form, just because you can't use that as what you're plugging in ingredients into, doesn't mean that can't be your final answer, or at least the form your final answer is in. Pause the video, of course, if you need to catch up with copying that down. But let's get into number 3. So again, ideally, if we can look at this and see not only the slope, but what the y-intercept is, then that's ideal, and that's going to be what, I mean, at least in my opinion, what I'm going to recommend and suggest that you do. So the slope, okay. Ooh, I wonder what points. Ooh. I mean, man, look, speaking of the y-intercept as well, looks like that's a nice point. And again, the farther apart, the better. Man, now that I'm really looking at this with fresh eyes, looks like there's a bunch of points. So like that one looks good. I mean, man, there's a lot. I wonder when I was coming up, let's see here. Looks like these are points. So 2, it looks like that is a point I would have picked, but man, I'm liking this one. 0 comma, is that 76? Ooh. This next thing I'm going to talk about might be the biggest reason for this entire example in the warm-up. Is this spot 76? It can't be, right? 25, 50, 75. Is every little... Are we jumping by ones here? No way. Is it by fives? 5, 10, 15, 20, 25, yep, 30, 35, 40, 45, 50. So this is going by fives. So this is actually 0 comma 80. And this would be, yep, I did pick this one. Well, this one at least. 20 comma 30. Okay, so I mean, I guess that answers our question. So look, getting our slope. Oh my gosh. So getting our slope, look, this is a really good approach, you know what I mean, using the formula to end up getting this as a slope. If you were going to count, you just got to make sure you're counting correctly. Like it's not 1, 2, 3, 4, 5 as you're counting down. It's 5, 10, 15, 20, 25, 30, 35, 40, 40, you know what I mean? You just got to make sure you're counting correctly. But the slope ends up being negative 5 over 2. The y-intercept looks like it's 80. So there's your equation. You know, you can go ahead and just plug those into y equals mx plus b. So that does it for the warm-up. Okay, so next we're going to go through what is basically the official notes handout in your notes packet if you got all the notes all at once in a packet, but the notes handout for 5.0b. So this is going to be about lines of best fit, and this goes along with scatter plots. So this example here, to start off the notes, I think this notes handout is basically 2 examples, to do. And so part A here of the first example says, make a scatter plot of the data below, which is basically plot all these points. So this is not your typical looking vertical table. Normally tables are in columns, 2 columns, where one column is kind of like your x variable, like the left column would be like your x, the more independent variable, and the second column be more like your y or your more dependent. But a horizontal table is very similar. This is traditionally supposed to be your more like x-axis variable that's more independent, and then this is a little more dependent. So if you want to label this, in fact, probably should label this axis like visits, because so this would be like the visits, and this axis here, if you want to label it below, would be like the weeks, the number of weeks, and this would be number of visits right here. So I guess the first part is just to do your best to plot these points. Like the first point is 1, 2.3, and then the next point is going to be 2, 4.7, and so you just have to do your best to plot all those blue dots. You can pause the video, and whether or not you're doing this on your own, which you probably should, it's probably easier just to kind of try to plot these points yourself without just necessarily like looking where my dots are. But make sure to get the video paused and get these blue points down before you continue, okay? But here I am going to continue now. So now make a scatter plot, but does the scatter plot so when it comes to the directions don't necessarily mention, now part B, draw your line of best fit. That's going to be a pretty common thing in the directions, but to answer the questions from here, at least some of them anyway, or the rest of them, I don't know, well, at least C and D probably, it's going to be best to have what we call a line of best fit. So a line of best fit is like when you look at a scatter plot and the dots are not making a perfect line, like they're not all literally collinear and they're all on a perfectly straight line, but there's a trend there, there's a pattern to where they're kind of making like an uphill line trend or a downhill line trend. You can draw a line through them that kind of, again, this is not a confusing title, it's a line of best fit. Like what line would best fit these points? And I don't know, there's no exact science to it, like in high school. Like there's a rule of thumb that sometimes you hear about, whether like, make sure there's like an equal number of dots on either side of your line of best fit. I don't know if that's not a perfect rule of thumb, but I think you might, if it was really important to be exact with this line of best fit, you might need a computer to do it for you, to kind of take this data and then spit out, what the perfect line of best fit would be. But because everyone, if you just had to eyeball it, everyone would be drawing a different line. But here, for this example, so the reason I have this yellow kind of point emphasized is, let's have everyone put their line through, let's see, looks like 15 comma what? Oh, 30. Is it 15 comma 30? As well as 0 comma 0. So everyone, draw your line through 0 comma 0 and 15 comma 30, and let's just kind of all agree, for the sake of the notes, that this line is best fitting this scatter plot of data. Okay? So, quick question here for part B, pretty simple question. Does the scatter plot show a positive correlation, a negative correlation, or no correlation? Well, if you were paying attention and if you learned 5.0a, it's positive correlation. Next question. Predict the total number of visits to the website after 20 weeks online. Predict the total number of visits. So based on this data, based on the pattern here, the pattern of the points, maybe even the pattern of the line, what would have to be your prediction for the total number of visits after 20 weeks? Remember, weeks is this axis. So 20 weeks is, look, right here. So can you just basically, is it possible, is it realistic for you to just maybe eyeball where? Because here's the thing. It's all about, where is my line going to be? Like, this line of best fit is the best thing I have to kind of tell the story of where these dots are going. So if we just extended the line a little bit, would it be pretty easy to see where our line would be for 20 weeks? I think so. Looks like it would be up here, like right there, it would hit, which is 40 or 40,000 visits to the website. Get it? Just kind of look at where the line would be. Part D, predict the total number of visits to the website after, see, now we're getting a little more complicated. 52 weeks online. If you just kind of, well, where would my line be if we went all the way over to 52 on the x-axis or on the weeks axis? Now, especially for this example, that wouldn't be too difficult to kind of just wing it a little bit, like kind of going like, well, my line, like basically if you could just see what the slope is, which the slope at first glance looks like it's going up 1 over 1, but in reality, it's not going up 1 over 1. Look at how this axis is labeled. It's actually going up 2 over 1, 2 over 1. So it's going to keep this pattern going, and if you kind of just extend that number, like that numerical pattern, you're going to see that the slope ends up being 2, okay? Or you could just do, let's see here, 15 comma 30. Like, look, you could just do the formula for these coordinates right here and 0 comma 0. So 15 comma 30 and 0 comma 0. You could calculate the slope that way. And then along with the y-intercept of 0, that allows me to write the what? The equation. y equals mx plus b. If you know m is that and b is that, there's my equation, which you don't really need the plus 0. Just you can just kind of scratch the plus 0, and there's my equation, okay? And guess what? To make a prediction for something that's kind of off the charts, like way out of bounds, your equation, if you have an equation of your line, that makes things really simple. Because remember, your x value is basically a number of weeks, and your y variable, it represents the number of visits. So 52 weeks online, what are we going to do with this number 52 in the equation? We're going to plug it in for x. And believe it or not, you should believe it, that gets you the answer. So instead of just kind of like on a calculator or like in your head going, well, I see the slope of this, or I see how it's kind of going like this, and I can, again, in a sort of numerical way, figure out where this line's going to be when this is able to extend out to the right to 52 weeks, or you can get the equation of the line, literally the equation of the line, and plug that in for, in this case, x. So y equals 2 times 52, 104. Technically 104,000 visits. And that's the answer. So this is how we're going to make predictions a lot, using the equation. All right, the other example in this handout, once again, plot the data points. So starting with like -5, 123. So, I mean, if you want to pause the video and try to plot these points yourself, I'll give you a chance to pause and plot. And then I think the next part's going to be draw a line of best fit, but you might want to hold off on that. But for right now, make sure you pause if you want to and plot the points. All right. So here's the points that I put down for this chart. Just again, hopefully do your best, or you did your best. And now again, it's time to draw the line of best fit. Like, what exactly, line? Everyone, if left onto their own devices, would probably draw like a slightly different line. So I'm going to kind of make that decision for you, which will happen a lot, even on like the Keystone exam. They'll kind of say, well, here's the line of best fit. The line of best fit is the line that passes through 20,760. Geez. 20,760. The way this is. Let's see here. So that's 700. 720, 40, 60. Man, I mean, you're going to have to kind of manage for yourself. Where's 7? Okay, so here, look, this is going by 20s if you haven't noticed. 20, 40, 60, 80, 100. So this is 720, 740, 760. Okay, good. Now 0, 200, that's a little bit easier. 0, 200. And so again, I'm saying that we're all going to agree that our line of best fit for the purple dots will pass through those two orange points. Okay? So again, pause the video if needed to get this line of best fit finished. So there's the line of best fit. And now, again, look, literally, they want you to figure out the equation of this line, which we've done before many times, including the warm-up for today. And look, thinking ahead, why are we going to be doing this? So we can make an estimation in the final problem. So again, going back to the warm-up, to come up with the equation, if we can figure out the slope and the y-intercept from this graph, that's what we want to do. And so kind of fast-tracking this now. Again, you can count carefully, 20, 40, 60, 80, 100, 120. If you want to count the rise over run, be my guest. But using the formula is probably the what you want to do. If you have these coordinates of these two orange points. Again, okay, I got to say this. When you're picking points to come up with a slope and so you can get the equation, these purple points, they don't matter. Like, they mean diddly squat now. Once we have our line of best fit, all that matters is what points are on the line. And hey, if one of your purple points happens to be on the line, you can use one of those. I don't think any of these look to be on the line good enough. So you got to pick points that are on the line. And it's very possible, in fact, very likely, that you're going to be coming up with new points, none of which were in this table, okay? So we're going with these orange points, and the slope ends up being just a very nice 28. 560 divided by 20, that divided nice and clean. And then what else? Remember, what else do we like to have to run an equation? Slope and y-intercept, which is clearly 200. Well, at least in our line that we drew. And so again, what's the equation? Y equals 28x plus 200. And now, to do this next problem, using your equation, estimate the number of skiers that would be out on a 37-degree day. Again, you could extend this line in a sort of numerical way until it would line up with 37. Like you could do, well, it's jumping like this every 5, whatever. Sometimes it's easier than others times. But I'm telling you, if you have the equation, okay, the equation does that with the line. And is 37 degrees, is that more of like an x value that they're giving us or a y value? It's 37 degrees. So, okay, so this was number of skiers, and then, so this is so 37 is an x value. So plug it in for x. And then all you got to do then is literally 28 times 37 plus 200. And hopefully I'm not wrong with any of this math. You end up getting 1,236 skiers. Which again, I think the last thing I'll say here is it definitely is an estimation. And the reason we can definitely call it an estimation is because the line was an estimation. We didn't have a computer draw this line based on the data, the points. So the line was an estimation. So yeah, this is an estimation. And I believe that does it for that handout. Okay, so the last handout in this video is the examples for the extra examples for 5.0b, which hopefully a lot of things are just going to be reviewed, and so this all kind of comes full circle, and we can kind of almost like a nice summary of everything that's important to understand. But also on that note, we might not be doing this on the same day in class we did that notes handout that we just went over in this video. So if you, let's say you're only absent one day or something, and you missed going over this stuff, if you're, say, coming back to school tomorrow or for the next class, we might be doing this in class when you come back. But anyway, you know what I'm saying. Probably going to be doing this the class after we did this. But we're going to include it in this video, because why not? All right. So again, hopefully I'm just going to be kind of like hitting some of the same notes again, and we can go through this kind of quickly. So here we go. Hopefully this is going to be very, I don't know, make a lot of sense to you now that we've done everything else we just did. So here we go. Question 1, example number 1, and here's the scatter plot, and it's about escape time in minutes and like the size of it. So it's like an escape room, and these are like the group sizes. Anyway, so apparently like this data came from, well, there was this one group where there was maybe 5 of them, and it took them like just over 15 minutes. And so this point represented some group of 5. This point represented some group of 8, it looks like. This point right here must have been a group of 13. And then this line of best fit was drawn. And so the question is, predict how long it would take a group of 10 people to escape the room. And a little bit of subcontext here, or the teaching point. Does it matter that there's already a data point for 10 people? Like if we had a table for this, you would see that a group of 10, it took them 12 minutes. Like this data point was from a group of 10 people, and it took them 12 minutes. But is the answer 12 minutes? If we had to predict how long it would take if like another group of 10 walked into the escape room place or the escape room and tried it, would it also take them 12 minutes? Or would you go with what the line of best fit is saying? You would go with the line of best fit. Okay, and so like here is what you would go with for a prediction for 10 people, and the number of minutes looks like 8 minutes. So a pretty simple, quick question. You know, it's not like they were asking for a group of like 30 people, way out of bounds. You can just look at the line and see where the line is for 10 people, and it's over here, look, at 8 minutes. All right? And here's something new that I might, kind of point out, no pun intended. Speaking of like, well, how long would it take a group of 30 people? If you actually figured that out, right, think about it. Where would this line be going, and what is sort of the answer for the number of minutes it would take a group of 30 people? If you just go with like literally what the line is telling you, you're going to get a negative answer. Like you're going to get negative something minutes, which of course is preposterous. Like that doesn't make any sense. So oftentimes with like these real life, graphs with real life variables, the equation, the line only makes sense for part of it, or because obviously once we get to like, well, how long would it take a group of, and it looks like 11, 12, 13, like 14 people, it would take them less than 0 minutes, which is, it doesn't make any sense. So anyway, kind of just be aware of that. Like even this one, this scatter plot represents the number of games pitched along with the number of strikeouts that you have, as a pitcher. You would think that this line would have to start at 0, 0. The fact that this line doesn't start at the origin, because right, If you pitch 0 games, wouldn't you have 0 strikeouts rather than, I don't know, it looks like, where would this line be going? Like maybe to whatever this is, which, hey, is it 11 or something else? Look at how this axis is scaled and stuff and broken up. I think this is actually 12. So the fact that that is a point on our line of best fit here doesn't make a whole lot of sense, does it? Like in the context of, well, if you pitch 0 games, does that, you start off with 12 strikeouts? I don't know. So that doesn't seem to make a lot of sense. But anyway, the actual question here is, once again, a prediction. Predict the total strikeouts for a pitcher who's pitched 36 games. Well, again, you can kind of go, well, 36 games, this line is heading to what as it kind of goes up this many, as it goes over this many, which again, you're kind of talking about the slope when you're thinking about that kind of a thing. But we're going to get the equation to make this prediction. So again, what do we want to know for an equation? Not only the slope, which ends up being 8/3, whether you did that by counting or with a formula, using coordinates. The slope of this line ends up being 8/3. And hey, if you just extend this line a little bit, it does end up being basically 12 or close enough for, again, even if you're doing an approximation with these, it's more than okay. And so absolutely you can say that the y-intercept is 12, which just means the equation is that. But again, why do we want the equation? To make this prediction. Because if we're trying to figure out, what our strikeouts are going to be for 36 games, we can just plug in 36 in for X and then do this math. Even with a calculator, 8/3 times 36 plus 12, that equals 108. So that's the answer, even though this graph, you can argue, doesn't make 100% sense. The answer is about 108 strikeouts. Next example. Once again, a prediction. So again, just reviewing some of the notes from, well, the beats, the teaching points from the last handout. We got to make a prediction for 25 degrees. To do that, we're going to want to have the equation of this line of best fit, okay? So what can we do? We obviously need the slope. So I'm going to have you go with 90, 180, which is like there. 90, 180. And I'm also going to have you go with this point, it looks like a nice point, which, look, spoiler alert, I guess, but the coordinates of this nice point, aren't they 47.5? Because look at how this x-axis is labeled and scaled. If every 2 boxes are basically worth 5, then it looks like every 1 box is going by 2.5. So anyway, all I'm saying is that this ends up being 47.5, 60. Looks like this is going by tens. So you got to be very aware of that, okay? Because if you're going to count your rise over run slope, you got to be aware of how much you're counting by. It's not necessarily by ones, okay? But I think to be safe, again, this is nothing new, going with the formula, okay? And just doing like maybe 180 minus 60, y2 minus y1, all over x2 minus x1. And hey, here's something kind of newish for our notes and stuff. for lines of best fit, again, this is all like one big approximation usually. So if you want to just approximate your slope and round it to the nearest decimal, I am more than okay. I'm okay with that. Okay? All right, but anyway, moving on. Getting back to the overall point here, or like the overall process. We have our slope now. What else do we need? What else would we love to have to make our what? What are we looking to make? We're looking to make our equation. So what is amazing to know along with m? Well, b, right? Like, so is that our y-intercept? No, it's not. This right here is not our y-intercept, okay? Because the real y-axis is not even here. Look at this right here. Like right there. 70, 65, 60, 55, 50, 45, 40. This is really supposed to go 35, 30, 25, 20. The real y-axis is off the screen here. Okay? So basically what I'm saying is we don't know what B is. It's one of these examples where we can't just plug in, or it'd be really tough, or it's not easy enough for my money to plug into y equals mx plus b. We're going to plug into excuse me, the other formula, point slope form. And to plug into point slope form, you know, y minus y1 equals m times x minus x1, we need the slope and what? Just some other point, just some random point, any point, any point. I'm picking this one, 90, 180. So taking this point as well as this slope, this is what point slope form ends up looking like. Y minus y1 equals m times x minus x1. And again, this equal sign you can even write as an approximately equal to if you want. I mean, remember this 2.82 is absolutely an approximation. So I know that this equal sign is a little bit of a stretch. But anyway, so we have an equation, and like I've said many times, you might feel like, I want to stop here. You know, point slope form of an equation is good enough for me. Well, to make these predictions, it's actually a lot nicer if your equation ends up in slope-intercept form. Okay, and again, I'm thinking ahead to plugging in my 25, you know, to make this prediction. So here we'll fast track it, ... If I distribute the 2.82, you know, clear the bubble, and then I add 180 to both sides to get the y by itself. I think, and again, I hope I'm not making any mistakes here in this video for these notes. Okay, the slope-intercept form ends up being y equals, or approximately equals, 2.82x minus 73.8. And again, decimals are okay, more than okay, I think, with this line of best fit stuff. Right? So anyway, now we have our equation in this form, which again makes it really easy to get an answer after just plugging in 25 in for x. So what's my, again, what they're asking is like, well, what's your y value when your x value is 25? So you literally, you know, replace the x with 25, and then you do 2.82 times 25 minus 73.8, and you end up getting approximately, of course, negative 3.3 customers, which again doesn't make any sense, you know, like in realistic terms, like in reality, you know. Like, geez, when the temperature is... So, like, this data, this line of best fit kind of stops making sense at some point as it heads to the left. Because, again, it doesn't make any sense. Like, when it's 25 degrees outside, you have negative 3.3 customers. And this is just, you don't have this on your paper probably. You don't have this. But this is a pretty good illustration, like a pretty good visual of, like, if there wasn't a thing right here, this is what it would look like. So again, like, you go down to 25 degrees, look, the number would be negative 3.3, or better yet, the real y-intercept is like way down here. So what was the y-intercept again? Negative 73.8. So the actual y-intercept, negative 73.8, which now looks to be pretty accurate, right? But the last example you have on your paper, predict the amount of student loan debt for a doctor who is 30 years out of medical school. So here we have the vertical axis with your student debt. The horizontal axis is your years out of medical school. And again, this is just like, we don't have the actual table, but apparently there's a medical school graduate out there that, like, let's say this point right here, you know, this person has been 18 years out of medical school and has a certain amount of student loan debt, like probably $118,000. Let's see, this individual right here, so this data point was from another person, and apparently that person has been out of medical school for only 4 years. So it makes sense that they have more debt that they still haven't paid off yet because they've only been out of medical school for 4 years. And so this particular person has maybe somewhere between $130,000 and $131,000. But again, like, it's not a perfectly linear relationship, is it? Like, because everyone's different. And all these different, so that's why you get like a scatter plot, and heck, like, not all these points, if we just added more dots from like a survey, you might have a dot over here, and you might have a dot over here. Like, doesn't have to be all in this kind of negative correlation relationship. But anyway, let's get back to the example at hand. Here's our line of best fit, and we have to make a prediction. So we're going to want to have, since we're not asking about 15 years, we're not asking about 10 years, we're not asking about 7 years, where we could just kind of look on the line, we're way out of bounds here with 30 years. So it's nicest if we have our equation. And again, reoccurring theme is, do we see what the y-intercept is? Because ideally, we want to plug in for m and b in slope-intercept form. Is this our true y-intercept? Yes. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You know? So look at this here. All that means is that this is actually not where our x-axis is. Our true x-axis would be a lot lower, because this is like 120. But yeah, this is our y-axis. So we can just go with that, and all we need otherwise is the slope. So it looks like the points I'm going to have us use to figure out our slope is 0, 138, which happens to be the y-intercept also, and 15, 153. Wait a so disaster. It's not 153. It's 120. 23. No. No, 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 no. Oh, no. This is ruining the whole thing. This is going to be such a... Oh, no. It was a 2 all along. Oh, no. I think we need to fix this as we go here. 15 comma 123. Oh, no. Oh, no, oh, no, oh, no. Right? 0 comma 138, 15 comma 123. So, 123. I guess the good news is, there might be some good news. Let's see here. If we're doing 1... man, oh man. This might not be too bad to fix in real time. In fact, maybe I made like a double mistake here with stuff. So this, let's see here. So 120, okay, so these need switched. Man, that was like another mistake that I actually had it right originally and then I switched it, and so that's another mistake. But so this is supposed to say 123 minus 138, so y2 minus y1 all over x2 minus... The good news is this is right. Because this ends up being like negative 15 divided by positive 15. So, whew. Only had, I think I am good where I don't need to fix anything else. So that's a horrible looking 2. My goodness. Oh, jeez. Oh, jeez. Anyway. So anyway, once we have M and B, that's our best case scenario because there's our equation. Y equals negative 1x plus 138, mx plus b. And then we want to make a prediction for 30 years. Well, 30 is essentially an x coordinate. So plug that in, and then what is negative 30 plus 138? Positive 108. So according to our data, you know, our prediction for a medical school student, 30, this can't be realistic, but I mean, wow, 30 years out of medical school, still owes $108,000. Wow. I don't know how realistic that is for like real life people, but all right, so that does it for this entire video.